This clinical matrix compares 4 distinct scans of the same anatomy: a standard T1, an MRCP, a STIR, and a FLAIR. Protocol selection forces a constant prioritization of 3 specific outcomes: acquisition speed, spatial resolution, or tissue contrast. Inside the scanner, everything rests on the physical manipulation of billions of hydrogen protons. They precess in alignment with the primary magnetic field, awaiting the precise pulses and gradients that will encode their signal. Despite the variety of clinical protocols used in a modern radiology department, every scan's duration is governed by a single physical equation. This is the scan time equation. Total time equals TR multiplied by phase encoding steps multiplied by the number of signal averages. TR, or repetition time, is the mandatory waiting period between sequence cycles, allowing for necessary longitudinal relaxation. Phase encoding steps represent the total number of individual data lines required to fill the spatial matrix, and NEX, the number of signal averages, serves as a repetition multiplier used to increase the signal-to-noise ratio. Mastering these protocols requires deconstructing the baseline anatomy of a sequence and learning how to deviate from it to create GRE, IR, and TSE variants. These specialized sequences are mathematically engineered deviations from a core physical baseline. Every standard sequence follows a 5-step choreography designed to systematically fill K-space, the raw data matrix of the MRI image. Step 1 begins with the radiofrequency pulse. This sync wave represents the energy envelope used to excite the protons. This pulse flips the longitudinal magnetization completely into the transverse plane, where it can finally be detected as a signal. Step 2 occurs simultaneously. We apply the slice selection gradient to target a specific anatomical plane. To maintain phase coherence within that slice, the negative lobe of this gradient must be exactly half the positive lobe. Step 3 locks in the y-axis spatial data. Immediately after excitation, the phase encoding gradient is applied. This cycle must repeat for every single line in K-space. For a 256 matrix image, that means repeating the sequence 256 times, each with a different phase encoding strength. Step 4 is the signal readout. We apply the frequency encoding gradient to create an echo. A negative dephasing lobe is followed by a positive rephasing lobe. This forces the spins to realign and generate the signal echo at precisely the echo time, or TE. Finally, Step 5 concludes the cycle. The machine must wait for the TR to finish before it can repeat the process. This synchronized architecture of RF pulses and spatial gradients provides the rigid framework that all clinical sequences must either follow or intentionally modify. The baseline sequence is inherently inefficient. Waiting for T1 relaxation to complete creates massive gaps of dead time within every TR cycle. Multi-slice interleaving mitigates this by firing sequences for adjacent anatomical slices while the first slice is still recovering. While interleaving is standard, it doesn't overcome the physical speed limit if we need to image a single volume as quickly as possible. Turbo spin echo, or TSE, serves as the architectural bypass for this TR bottleneck. Instead of a single 180-degree rephase impulse per cycle, TSE applies a continuous train of them within a single TR. The total number of echoes generated in this cycle is defined as the echo train length. By varying the phase encoding gradient before every 180-degree pulse, TSE fills multiple independent lines of K-space in the time it would usually take to fill one. The haste sequence takes this logic to its extreme. Using a massive echo train length, often over 200, and half Fourier extrapolation, haste fills the entirety of K-space in a single cycle. This allows for ultra-fast, heavily T2-weighted imaging, which is the standard for MRCP studies. By utilizing a chain of 180-degree pulses, TSE transforms physical dead time into rapid data acquisition, sacrificing some contrast purity for significant clinical speed. Scenarios like dynamic, contrast-enhanced T1 imaging require even faster acquisition, demanding ultra-short TR times. In these millisecond-scale cycles, the standard 180-degree RF pulse physically takes too long to execute. The gradient recalled echo, or GRE, sequence solves this by deleting the 180-degree pulse from the architecture. GRE compensates by using the bipolar frequency encoding gradient to force the spins to rephase and generate the echo. To further accelerate the scan, GRE replaces the 90-degree excitation with smaller, variable flip angles. This allows the longitudinal magnetization to recover much faster. Abandoning the 180-degree pulse comes with a specific cost. The sequence can no longer correct for local magnetic field inhomogeneities. This results in T2 star weighting. While highly susceptible to artifacts, T2 star is essential for detecting the magnetic distortions caused by blood degradation products. GRE trades the homogeneity of true T2 contrast for extreme acquisition velocity and specialized susceptibility data. Many diagnostic challenges require the active subtraction of normal tissue signals, such as fat or fluid, to reveal subtle pathology. Inversion recovery sequences accomplish this by intercepting the T1 relaxation trajectories of specific tissues. The process begins with an initial 180-degree inversion pulse applied before the main sequence starts. This pulse drives the longitudinal magnetization of the tissues into a completely negative state. As the tissues recover, they return to positive alignment at different rates. Fat relaxes quickly, while fluid relaxes slowly, meaning they cross the zero axis at different moments. The strategy is to intercept the target tissue at the exact millisecond its recovery curve crosses the zero axis. Firing the 90-degree excitation pulse at this precise crossing means there is zero longitudinal magnetization to flip. That specific tissue yields no signal. This timing window is known as the time to inversion, or TI. Choosing a short TI of approximately 130 milliseconds nulls fat to create a stir scan. A long TI of about 2500 milliseconds nulls fluid, creating a flare scan. Inversion recovery effectively acts as an algorithmic subtraction technique, using physical recovery speeds to render interfering tissues invisible. These modifications show how the 5-step baseline adapts into a clinical toolkit. Gradient manipulations bypass the time limits of RF pulses for raw speed. Chaining rephasing pulses allows ultra-fast T2-weighted acquisition by filling K-space efficiently. Prefixing inversion pulses uses relaxation curves to delete specific tissues. Effective protocol management relies on precise understanding of how manipulating time, RF energy, and magnetic gradients translates physical spin states into diagnostic insight.